All right, in this lesson we're going to look at more examples related to the exponential rate of change. And the first one that we're going to look at is what's known as Newton's law of cooling. Again, this is one of those that fits into that y equals y sub 0 e to the kt type models. The only difference here is that instead of having a single value for y representing population, y sub 0 representing initial population, we have a difference, and the two differences that we're looking at are, in essence, our y is going to be the value of temperature minus the surrounding temperature of an object, and our initial is going to be the difference between the initial temperature and the surrounding temperature. So both of those take into account the surrounding temperature. Other than that, this is just a y equals y sub 0 e to the negative kt type model. Let's go ahead and look at our example here. The temperature of a cake was 350 degrees at the instant that it came out of the oven. After 10 minutes, its temperature is 200 degrees Fahrenheit. If room temperature is 70 degrees Fahrenheit, how much longer will it take for the cake to cool to 90 degrees Fahrenheit? Okay, so let's identify what these items are. 70 degrees, that's our room temperature. That's the surrounding temperature while this item is cooling. The 350 degrees here is our initial temperature, and the 200 degrees is our current temperature. And we need to use those in this context to find the value of K for this particular cake. Okay, K is a constant that depends on the material that's cooling. In this case, we're going to need to find the constant first before we can figure out how much longer it takes for the cake to cool to 90 degrees Fahrenheit. And our time that's going to go into this initial calculation is 10 minutes. So I'm going to go ahead and set this up. The temperature minus the surrounding temperature is equal to the initial temperature minus the surrounding temperature times e to the negative 10k. And I can use this equation to solve the k, and then I can apply that for other temperatures and times in the course of this problem. So I get 130 equals 280 e to the negative 10k. So 13 over 28 is equal to e to the negative 10k. Taking the natural log of both sides, we get that the natural log of 13 over 28 is equal to negative 10k. And so k is equal to natural log of 13 over 28 divided by negative 10. Now I prefer, instead of converting this over to a decimal, just because when we round things off in exponents, it can have big variations to our final answer. So I'm just going to leave this k value exactly as it is for my next calculation, which is going to be to figure out how long it takes to cool to 90 degrees Fahrenheit. How much longer? Okay, now since we're finding how much longer, in essence we're looking for the time starting with the temperature at 200 degrees. So I'm going to set up my model here. We want it to cool to 90 degrees. So 90 minus 70 is going to be equal to 200 minus 70 times e to the negative kt. So it's going to be e to the natural log of 13 over 28 divided by 10 t. So we've got 20 equals 130 e to that. A little hard for me to write small on here. So we've got 2 over 13 is equal to e to the natural log of 13 over 28 all that over 10 t. And we can go ahead and solve this for t by taking the natural log of both sides. And we get natural log of 2 over 13 equals natural log of 13 over 28 over 10 times t. And so t is going to be equal to 10 natural log of 2 over 13 divided by natural log of 13 over 28. Now I'm going to go ahead and calculate that. And we've got 10 natural log of 2 over 13 divided by natural log of 13 over 28. And so it should take 24.396 minutes. And that's how much longer it will take for the cake to cool to 90 degrees Fahrenheit. Alright, that's going to be it for this video. See you next time when we'll look at some more exponential applications.